the atomic theory. In this lesson, we're going to be talking about the atomic theory, atomic size, Democritus, and then three main theories that shape the way we think about atoms today: Dalton, J.J. Thompson, and the Bohr-Rutherford models. We're going to conclude the lesson by looking at Bohr-Rutherford diagrams. The atom. Materials can be subdivided into smaller and smaller particles. These are atoms. Atoms are the building blocks of all matter. Atoms are tiny. And to give you some perspective, if you line up 100 million copper atoms in a single file, they would be approximately 1 centimeter long. Sizing up the atom. Atoms, as I said, are incredibly small. The diameter of an atom ranges from about 0.1 to 0.5 nanometers. The diameter of a human hair is between 17 and 181 micrometers, which comes out to be about 1 times 10 to the negative 10 meters to about 5 times 10 to the negative 10 meters. In contrast, the diameter of a human hair is between 1.7 times 10 to the negative 5 meters and 1.81 times 10 to the negative 4 meters. You could fit 170,000 atoms across the width of a human hair. Here's another way to look at it. If you take the size of the Earth and compare it to a soda can, you can use the same ratio to compare a soda can to an atom. That's how small atoms actually are. But despite their small size, individual atoms can be observed with instruments such as scanning electron microscopes. This image here is a scanning tunneling microscope image of gold. The individual atoms composing the material are visible. You can see the individual atoms composing the material. They're arranged in columns several atoms wide with regularly spaced pits between them. And if you look carefully, you can see our columns here. And you're going to see that there's going to be like 1, 2, 3, 4 to 5 atoms all the way across. And then you're going to have these pits between them, these black areas here. So what I'd like you to do is pause the video and watch number 1 and 2. They're going to give you a really good perspective of how small atoms are. Democritus. The Greek philosopher Democritus lived between 460 BC and 370 BC. He was among the first to suggest the existence of atoms. Keeping in mind back then, there was no way for them to know atoms existed, nor was there a way for him to prove his theory. He believed that atoms were indivisible and indestructible. Then along comes Dalton many, many years later. In fact, his model didn't originate until the 1800s. He referred to the atom as a really small, hard, indestructible sphere that could not be subdivided. He also said that different atoms have different properties, and that the atom is the smallest particle of an element. An element, on the other hand, is a substance made up of only one type of atom. So to give you an idea, his model would look like this, with an oxygen atom being this blue sphere and a hydrogen atom being this red sphere. Small, indestructible spheres that couldn't be subdivided. In 1897, J.J. Thompson demonstrated that there were negatively charged particles found within atoms using cathode ray tubes. After further investigation, he concluded that the same negatively charged particles are found in all atoms. These are called electrons. And this is in contrast to Dalton's theory, who said that they were small, indestructible spheres, and that was the smallest particle that there were. Along comes Thompson and says, no, that's not quite right, because inside these spheres are these negatively charged particles. And the bottom here, you'll see a picture of J.J. Thompson's cathode ray tubes. So using these tubes, he found that the cathode rays, these blue lines, could be deflected by an electric field. That's this yellow part right there. Since we could deflect the cathode rays using an electric field, that cathode ray must contain some kind of negative particle that would be affected by the electric field. Now, Thompson knew that atoms didn't have a positive or negative charge, and since his particles were negative, he knew that there must be positively charged particles within the atom as well. So here's Thompson's atomic model. So Thompson believed that the electrons were like plums embedded in a positively charged pudding. It was called the plum pudding or raisin bun model. So you can see here we're going to have electrons and protons, the positive ones, spread evenly throughout the atom. Then a few years later, in 1911, Ernest Rutherford did his famous gold foil experiment. What he did was he shot positive particles, these alpha particles, from this black box here, at a thin sheet of gold foil, which is represented by this yellow guy right there. Particles that hit the detecting screen, blue film, were recorded. So this blue part here, that's the detecting screen, and it's going to wrap all the way around. Now, Rutherford's hypothesis, based on the plum pudding model put up by Thompson, was that some of the alpha particles be slightly diverted due to the avoidance of other positive particles inside the atom. So they'd come near these positive particles here, and they'd be slightly deflected. So it would look something like this on the left. We're getting some of these particles being deflected, some of them are going straight through, but for the most part, their path would be unaffected. What he actually found was that Thompson's model was right most of the time. Most of the particles were only slightly deflected. However, every once in a while, one was significantly reflected back to where it came. And you can see that represented by this guy right here. Therefore, they must have collided and rebounded off something very dense inside that gold foil. So I'd like you to pause the video and watch number 3. It shows you the gold foil experiment. So most of the particles passed right through, but a few were deflected. Very few, 1 out of every 8,000, were greatly deflected, as in they bounced straight back almost at the alpha emitter. And he said it's like shooting bullets at tissue paper and watching them bounce back. That's how surprising it was. So based on his experimental evidence, he concluded the atom is mostly empty space, represented by this beige color here. It contains a small, dense, positively charged nucleus at the center, that's the black, and negatively charged electrons revolving around the positive nucleus. So basically, it looks like this. Keeping in mind, any alpha particle that hit this center would be deflected back. Now, since that center takes up so little space, most of the time the alpha particles just went straight through, or were slightly deflected because they got a little bit too close to the positive nucleus. Now along comes Bohr in 1912 and says, if there are negatively charged particles around a positively charged nucleus, why don't they attract and collide? Why don't these negative electrons get sucked into the positive nucleus? So Bohr and Rutherford got together and produced a new theory in 1913. In this theory, there's a central positive nucleus, and electrons are moving in orbits or energy levels around the nucleus, kind of like how satellites revolve around Earth and how Earth revolves around the Sun. Electrons mostly stay in their orbits unless a change in energy causes them to move. If you give energy to the electrons, then they're going to go up in energy level. And that brings us to our Bohr-Rutherford diagrams, which are an effective way to represent the first 20 elements. Each electron orbit is shown as a ring around the nucleus. The first orbit will hold a maximum of 2 electrons. The second orbit will hold a maximum of 8, and the third will hold a maximum of 8. Now we're only going to do the first 20 elements. So if you have 8 plus 8 plus 2, that's going to be 18. That means that the last orbit can only have a maximum of 2 electrons, based on this theory. And here are 3 examples of Bohr-Rutherford diagrams. Sodium would look like this. We're going to have 2 here, right? 1, 2, and then you have 8 around the second. 1, 2, 3, 4, 5, 6, 7, 8, and then it has 1 left over. Helium only has 2 in its outer orbit, and neon has 8 in its outer orbit, plus the 2 in the inner orbit. So how do we draw Bohr-Rutherford diagrams? Number 1, we're going to determine the number of electrons. That's going to equal the number of protons, which equals the atomic number. We're going to determine the number of neutrons, and we're going to draw a circle and write the number of protons and neutrons inside. Keeping in mind to find the number of neutrons, that's going to be the mass minus the number of protons. We're going to write the element symbol underneath, so for example, sodium, and we're going to place electrons in their proper orbit, 2, 8, 8, and we're going to add them individually, north, south, east, west direction, and then pair them up as any electrons are left over. Once the maximum orbit is reached, then we're going to go to the next orbit. So let's see an example for sodium. The number of electrons equals the number of protons, which equals the atomic number, which is equal to 11. The number of neutrons is equal to the mass minus the number of protons. That's 23 minus 11, so that's 12. And then we're going to draw our nucleus. You can see here our nucleus, 11p, 12n. So that's going to be drawn right there. And then around, we're going to put our electrons. We're going to put 2 electrons in the first orbit. So we got 1, 2. We started with 11 minus 2. We have 9 left over. We're going to put north, south, east, west, and then we're going to start pairing them up. North, south, east, west. 9 minus 8. We have 1 left over. I'm going to put it out in the top here. Keeping in mind in the first orbit, we're going to pair both of them. We're not going to do the north-south. So you can see these 2 guys are going to be paired. And that's going to represent the fact that that orbit is full. If an atom has 2 electrons, then it's not going to make any bonds. And that's going to be represented by these 2 electrons being paired together. So what I'd like you to do is pause the video and draw the following Bohr-Rutherford diagram. So I want you to try lithium. Lithium has 3 electrons. So we're going to start by writing lithium underneath. We're going to draw the nucleus. We're going to write 3p. We're going to find out the number of neutrons. Now the mass of lithium is 7. So the number of neutrons is going to equal to the mass, 7 minus 3, which is equal to 4. So we're going to say 4n. We're going to draw our first orbit. We're going to put 2 electrons in there. We're going to draw our second orbit. I'm going to put the remaining electron right there. And then we're done. Again, pause the video and draw the Bohr-Rutherford diagram for carbon. So one of the first things you're going to need to do is figure out what the mass of carbon is. Now, once you look at the periodic table, you'll find out the mass of carbon is 12. So we're going to write C on the bottom. We're going to write 6p. We're going to write 6n because number of neutrons is going to equal to 12 minus 6, which is 6. And we're going to enclose the nucleus. Then we're going to draw our first orbit, and we're going to put 2 electrons right there. We started with 6, we used 2, we have 4 left. We're going to draw our second orbit. And we're going to go north, south, east, west. We've used all 4, we have 0 electrons left, and we're done. The one thing you need to keep in mind when you're figuring out your mass is that we're always going to round our mass. So for instance, carbon is going to be closer to 12.0107, so we round it to 12. One more time, I want you to pause the video and draw the Bohr-Rutherford diagram for potassium. Now the mass of potassium is 39.098, and we're going to round that to 39. We're going to write K underneath because that's the symbol for potassium. We're going to write 19p, and we're going to write something n. How do we figure out the number of neutrons? That's going to be 39 minus 19, which is equal to 20. So 20n. And then we're going to draw our nucleus. We're going to draw our first orbit, and we're going to put our 2 electrons, 1, 2. We're going to draw our second orbit. We started with 19, we used 2, we have 17 left. So we're going to go north, south, east, west, north, south, east, west. We used 8, we have 9 left over. We're going to draw another orbit. We're going to go north, south, east, west, north, south, east, west. We used 8, we have 1 left. So we're going to draw 1 more orbit. And we're going to put our last electron right there. And we're done. So before we finish, I want you to keep in mind that over the course of time, the Bohr-Rutherford model has been improved and altered as we've learned more about the atom. However, it's still an effective way to visualize and begin your understanding of the atom. And that concludes our lesson on the atomic theory.